Welcome class to our first video notes section on 4.5. We are finally going to start looking at some techniques for doing what's called a U-substitution. So what is a U-substitution? It is a technique that allows us to integrate a composition of functions, something that looks like this right here, where you've got one function g of x that's been plugged inside a larger function f. So a lot of times we'll call that function u, right? G of x will be u. So we'll think of f of g of x as f of u, which is basically a composition of functions. So I don't know if this rings any bells, but we kind of did a similar process back in chapter 2, and it was called the chain rule. The chain rule was what we used when we were trying to find the derivative of a composition of functions. Same scenario where I had one function plugged inside a larger function, or just another function. And the chain rule basically said, okay, to take the derivative of this composition of functions, one function inside another function, you take the derivative of the outer layer first, keeping that inside function intact and plugged in. But then you got to multiply that outer layer derivative by the derivative of the inside. So we kind of remember that, okay, if there's ever anything other than plain x plugged inside my functions, then when I'm taking the derivative, I have to multiply by the derivative of that thing that's inside, that's other than plain x. That's why we refer to it as like some other function of x. So here's the thing, now that we're doing integrals, which we now understand is the antiderivative, right? We're anti-differentiating, we're undoing the derivative or going backwards. We're going to think of U-substitution as the reverse chain rule. It's anti-differentiating the chain rule, so it's going backwards. So we kind of know what to look for, so to speak, because if you've used the chain rule on a function to take its derivative, you'll have this like extra piece, this derivative of the inside that's also being multiplied to your function. So oftentimes when we're doing U-substitution, that's kind of what we see in our integral. We see a function on the inside of some other function, and we'll see that its derivative, the derivative of the inside, is being multiplied to that function. That is an indication that a chain rule must have been done to take this derivative, and so when we go backward, we're going to have to use the reverse chain rule or a U-substitution. Oftentimes we think of, or we like to call the inside function u, and when we take its derivative, we'll see the g prime x being multiplied to the dx. And we'll think of that as an integral f of u du. We're going to completely change variables from x into u. But it all starts with identifying. We have to learn how to correctly identify u and then use that to find du. So there's a couple things we look for. Notice that u is the g of x. It's the function on the inside. So when we're trying to identify u, we first look for the function that's on the inside of another function. So these again are qualifications for finding u. So in this first one here, my eye kind of is drawn to this 3x plus 1 because it's inside this squaring function. So I'm going to choose that at first. And I'm not choosing the whole function, right? I don't want to let u equal f of g of x. I just want to let u equal just the part on the inside, just the 3x plus 1. And then this would turn into u squared, right? Because it's right now it's 3x plus 1 squared, but if I call u 3x plus 1, then I can think of this as u squared. And that's okay, right? It's okay to have an integral of u squared. Now to know for sure if that's the correct u, there's another qualification I'm looking for. Since we're saying that u is the inside function, this guy right here, then its derivative should also be present in the integral. So we're also looking for the function whose derivative is also present in the integral. So I'm going to take the derivative of u with respect to x, and I see that that would equal 3. That is confirmation to me that I chose the correct u because 3 is also there in the integral. So I chose a function that was inside the squaring function, and whose derivative of 3 was also present in the integral. That is an indication to me that I chose the correct u. Now when I'm solving for du, I want to multiply the dx to the other side. So my du in this case would equal 3 dx. That would be my derivative of the inside function times gx, right? Or sorry, times dx, which is what you see here. Du is the derivative of g was that inside function, that u is equal to, and then times dx right there. Let's look at part B. So part B has an exponential function. So when we're looking for the inside of an exponential function, we tend to look at the exponent area. So the exponent area is the inside of an exponential function. So in this case, I'm thinking u is going to equal 5x. That's my initial guess because it meets the first qualification. So then I'm going to take the derivative of that with respect to x, which would just be 5, and then that's my confirmation that I chose the correct u because 5 is also present in the integral. Then I'm going to multiply the dx to the other side because it did ask me to identify du, and du is what you get after you multiply that dx over, so du is equal to 5 dx, and u is equal to 5x. Why don't you guys try it in this section here? Okay, so for part A, if Ri is looking for the inside of another function, it's drawn right here to the inside of the squaring function. So I'm going to let u equal 2x squared plus 1. The derivative of that would be 4x, which is also there in the integral, which is my confirmation that I picked the correct u. And then to solve for du, we just bring the dx to the other side. So it's just the derivative of u times dx. In B, B is a little bit tricky because you might say, well, secant is the function that's on the inside. So I'm going to put a little star by qualification number 1. U doesn't have to be the inside of another function. It often is, but it doesn't have to be. And in this case, I can let u equal tan x plus 3 because its derivative, du, is equal to secant squared x. So because of that fact, that's the second qualification, which is really an important one. Because the derivative of tan x was in the integral, then it makes sense for me to use that as my u. And this here was my confirmation of that. So now we've had a little bit of practice identifying u and using that to find du. What we need to do now is learn how to completely integrate these. And so that's going to require a complete and formal change in variables. It's like a changing of the guard from dx to du. Because what I eventually want to do with this u that I'm using is integrate with respect to it so that I can easily use the antiderivative formulas we have for functions with a single variable, a single input, not a function inside a function. So I have to get rid of all x's and completely rewrite the integral in terms of u and du. That means I cannot leave any more x's or any variables other than u in the integral. So let's go back to those same integral setups we just saw in example 1, and let's learn how to actually go ahead and integrate them. So it starts by identifying u. And in this case, we had already decided u was this inside part here. U was my x squared plus 1. So then du is going to be 2x, or I should say, sorry, derivative of u with respect to x is going to equal 2x, right, using the power rule. I bring the dx up here, so du is equal to 2x dx. Now, some of you might look at this and say, oh, okay, I can see right now that this is equal to u squared du, because the x squared plus 1 has been replaced with a u, and the 2x dx has been replaced with du. If you can see that and make that leap, more power to you, go ahead and do it. But what I want to show you is a technique that can be used in all situations as they start to get more complicated for replacing dx with du. So what I do is I actually isolate the dx to get it in terms of du. So in this case, I would divide actually by the 2x. And I would say that du divided by 2x is equal to dx. So that when I do the complete changing of the variables from dx to du, I can substitute item by item. So I know that x squared plus 1 can be replaced with u. I know that dx can be replaced with du over 2x. So what I do is I kind of go piece by piece. The thing that's going to go inside the squaring function is going to be u, because I can use that instead of x squared plus 1. I have nothing to substitute the 2x with if I'm doing it this way, so I just leave it there. And then I know that my dx can be replaced with du over 2x if I'm using it this way. So I just replaced x squared plus 1 with u, and I replaced dx with du over 2x because I can see here that that's what dx equals in terms of u. Then what I notice is that the 2x's cancel out when I do it that way. And if you do this process, that's what you want to look for. You want to make sure that everything that had an x gets removed by substituting in this expression for dx. If somehow that didn't cancel out when I substituted in my expression for dx, then that means I did something wrong earlier with choosing my u or finding my du. So anyway, after I completely replace my function and my 2x dx with u squared and du, now I can just treat this as an integral with respect to u. That means I can just go ahead and use the power rule of integration, but with respect to u versus x, because that's what this du is saying that I can go ahead and do. So the power rule just says you add 1 to the power and then divide by that, and then we have to always add our constant of integration. And then all I have to do at the end is just take that expression that I had u equal to and plug it back in. So at the very end, I basically resubstitute to get my answer back in terms of x, because that's ultimately what I'm trying to find. I'm ultimately trying to find the value of this integral in terms of x. So I come back to here, I put back in my x squared plus 1. I go ahead and add those powers, so that's 3 plus c. And so that is my final answer. That's my antiderivative to this integral. Now, when you're first doing this, you might not feel 100% confident, so you're always welcome to check your answer by just taking the derivative of it. I can check and see if this is the correct antiderivative by seeing if this is its derivative. So I'm going to go ahead and do that now. So I have to use a chain rule though, right? You'll have to do that with these because these were reverse chain rules. So when you're checking with the derivative, you've got to use a chain rule. First, I'll start with the power rule though. Bring the 3 in front, and the constant multiple rule, which says this is like a 1/3. So 3 in front and then times 1/3, and then times x squared plus 1 to the power of 2, right? Because you subtract 1 from the power. But then I'd have to multiply by the derivative of the inside, which is 2x. That's the chain rule right there. Well, the 3 and the 1/3 would cancel, and I would just be left with x squared plus 1 squared times 2x. That was exactly what I had as the integrand in my original integral, which means that this is in fact the correct antiderivative. Okay, so then for b, again earlier we had found that u for this one was 5x. We had found that du dx, or the derivative of u with respect to x, was 5, and then we brought the dx up. So we know that u is 5x, and we know that du is 5 dx. So some of you might be able to see this, see the 5 and the dx, and go, oh, this is just e to the u du. If you can make that leap, again, more power to you. But I'm going to go through the process where I isolate the dx, and I kind of just replace each thing one item at a time. So I'm going to divide by 5 over here, and I'm going to say that du over 5 is equal to dx. So I know that I can replace 5x with u, and I know that I can replace dx with du over 5. So I'm going to go item by item and make that replacement. For the 5, I just sort of leave it there because I don't have a replacement for that yet. But where the 5x was, I'm going to replace with u because they're equivalent to each other, they're equal. And where the dx was, I'm going to replace with du over 5 because this little equation here tells me that they're the same. They can be used interchangeably. Then what I'm going to notice is that these 5's cancel out. And I'm just left with the integral of e to the u du. So now this is ready for integrating because I can take the antiderivative of e to the u with respect to u, which is just e to the u plus a constant. That's our antiderivative formula for e to the x with respect to x. I just use the same formula here because I'm basically treating u like x because I'm taking the integral with respect to u, which kind of makes u like the x in all of our formulas. So basically you can use all those formulas and just have them in terms of u. But when we do get to the end, we do want to resubstitute that 5x back in for u. So my final answer for this one would be e to the 5x plus c. Now a quick derivative check would show that this is in fact the derivative of e to the 5x plus c, which means our answer is correct. Why don't you guys try A and B? Okay, so in the first u try, I hope that your eye was sort of drawn to the inside of this cube and let u equal x squared plus 1. When you take the derivative of it, you get 2x dx, which should hopefully be confirmation that you chose the right u because its derivative is elsewhere in the integral. Then you can either just go to this step here, or you can isolate the dx and then substitute in u in place of x squared plus 1, and then du over 2x in place of dx. The 2x's then cancel, and you're left with this integral, 1 over u to the third du. I use the power rule for integrals to get here, and then I resubstitute at the end to get this final answer. And don't forget your constant of integration. For B, we had decided to let u equal tan x plus 3. So then du would be the derivative of tangent, which is secant squared dx. I can isolate dx to get du over secant squared. So then I can kind of substitute item by item. I had no substitute for secant squared, so I left it. I replaced tan x plus 3 with u, and I replaced dx with du over secant squared, which then removed the other secant squared, which was confirmation that I was doing this correctly. So all I had left in my integral was u times du. So I just did the antiderivative for u, which is basically a power rule, u squared over 2 plus my constant of integration, and then I resubstituted my tan x plus 3 at the end into my final answer. Now, moving on to example 3, again I have a kind of another unique situation where I don't really have any inside function, but I do notice that e to the x plus 1 is the derivative of e to the x plus x. So I'm thinking to let e to the x plus x be my u, because then du would be the derivative of that, e to the x plus 1, and then times dx. So I'm going to start skipping that middle step. I'll show you one last time here. So what I'm doing is I'm saying, okay, the derivative of u with respect to x is, and then I just take the derivative of this expression, e to the x plus 1, and then I multiply the dx to that. So then I get du is equal to e to the x plus 1 times dx. So basically I'm just going to start skipping that step, and I'm going to just find the derivative of the expression and then multiply it by dx. Then I'm going to do the process where I isolate dx by dividing by whatever is in front of it to both sides. And then I like to replace each term in the integral item by item. So I don't have a replacement for e to the x plus 1, but I do know, or I am saying, that u is equal to e to the x plus x. So I can replace e to the x plus x with u. And then I can replace dx with du divided by e to the x plus 1. So that will go in place of dx. And then what I'm hoping will happen, or what I'm making sure will happen, is that any item with an x in it will remove itself from the integral by canceling with whatever was here with my du expression. So in my integral, I should only have items with u left. And I do, because I only have a u and a du left over. So now I can just take the derivative, or excuse me, the antiderivative of u with respect to u, which would just be u squared over 2 plus the constant of integration. And then again, I can just resubstitute the e to the x plus x back in for u at the end to have my final answer. Now again, that one was kind of a little bit odd. It's just kind of a weird feel to it. So why don't we check our answer? So whenever you're not 100% sure, just take the derivative of your answer and see if it equals the integrand. So I'm going to have to use a power rule and a chain rule on this function here. So I would take 2 times e to the x plus x over 2 to the first power, right? Because you subtract 1 from the power, derivative of a constant is 0. And then I'd have to, oh wait, I forgot to multiply by the chain rule, right? I have to multiply by the derivative of this inside part, which is e to the x plus 1. And then derivative of a constant is 0. Okay, so then the 2's would cancel out, and I would be left with e to the x plus x times its derivative, e to the x plus 1, which is exactly what I had in my original integral, which tells me that I did this antiderivative correctly. So let's try the one in part B. So again, my eye is just sort of drawn to under the radical sign because it's inside. So whenever there is an inside, I tend to go there to pick out u. So u is x squared minus x cubed minus 2. So then the derivative of u would be 3x squared and then dx. So then if I'm isolating dx, I could say that du over 3x squared is equal to dx. And so now I can substitute item by item. I'm going to change out x cubed minus 2 for u. I'm going to change out dx for du over 3x squared. So when I'm converting my integral, I still have the 3x squared in front because I didn't have a change out for that yet. But now I'm going to put u under the radical because I know that, or I'm saying that x cubed minus 2 is equal to u. And then in place of dx, I'm going to replace that with du divided by 3x squared. So the 3x squareds cancel out as they should to leave me with an integral having only expressions with u in them. So I end up with the integral of the square root of u du. I'm going to think of that as u to the 1/2 power du. So I can take the antiderivative of that with respect to u by using the power rule for integrals. So I add 1 to the power, divide by it, add a constant of integration. So that's 2/3 u to the 3/2 plus my constant of integration. And then I will resubstitute my expression for u, which is x cubed minus 2, back in at the very end for my final answer. So for this one I get 2/3 times x cubed minus 2 to the power of 3/2 plus c. Now, in example 4, we're going to take a look at some special cases where things don't always work out perfectly, but they can still work out. So I'm going to follow the same procedures I've been using so far, but just kind of show you what to do in certain special cases. Okay, so in this integral, I notice the inside looks like it's x squared plus 1. That's inside the square. So the derivative of that would be 2x dx. So you might be thinking, wait, that derivative is not elsewhere in the integral. And I would say that enough of the derivative is in the integral. I still have the x dx, which is a confirmation. So as long as your derivative only differs by a constant from what's in the integral, then you're fine. So this is where it becomes helpful to just go ahead and isolate the dx and say, well, I know that du over 2x would equal dx, and just kind of replace dx with that expression. I can take this integral over here and say, well, the x is still there, but I can replace the x squared plus 1 squared with u, right? We're saying u is equivalent to that, so I can replace it. And we're going to replace dx with du over 2x. So the 2 doesn't cancel, but the x does, and that's all that matters. So it's okay if you have an extra constant in your derivative. And when I say extra, I mean something that was in your derivative that wasn't in the integral. Because remember that rule that we had learned, I think it was section 4.1, where if you have an extra constant left in your integral, think of this as 1/2, you can just pull it right on out. So this is 1/2 times the integral of u squared du. And so then I can go ahead and take the antiderivative of u squared with respect to u. I just have to make sure to multiply that by 1/2. So 1/2 times u to the third over 3 plus my constant of integration. Or u to the third over 6 plus my constant of integration. And then I just resubstitute at the end, just like normal. Take my x squared plus 1 and plug it back in there. So I get x squared plus 1 to the third all over 6 plus c. And again, you're always welcome to check by taking the derivative of your answer to see if it matches your integrand. So let's take a look at b. So again, our I is kind of drawn on the inside here. And so I want to let u equal x squared plus 1. So then I want to take the derivative of that, which is 2x dx. And then right here, you should notice that there's a problem because I have an x in my derivative and I have no other x anywhere else in this integral. It's not there. No other x. So when I go to isolate my dx, right, and replace item by item, I run into a problem because I would get the integral of u squared, because I would replace x squared plus 1 as u, and then I would replace dx with du over 2x, and then I would run into a giant problem. I have an x in my integral and I have no way to get rid of it. You can't pull a variable out of the integral, only a constant. So in this case I would go, oh wait a minute, I can't do a u-substitution here. I'm going to have to use some other process. The u-substitution didn't work. I wasn't able to completely remove all x's. So instead, for this one, we would have to revert to foiling it. It's not too much work of a foiling in this particular case. It'd be x to the fourth plus 2x squared plus 1, and then just take the antiderivative with respect to u. So x to the fifth over 5, 2x to the third over 3 plus x plus a constant. And that would be our antiderivative for that one. For c, again, our I is drawn to the inside, or should be. So u would be that item under the radical sign or inside the radical. And then du is just 2. And again, that's okay. It is okay to have an additional constant in your derivative. Additional meaning something that's in the derivative that was not anywhere in the integral, right? There's no 2 outside of the radical and in the integral. So, but that's okay. It's okay to be off by a constant. I'm just going to go ahead and divide both sides by 2 so I can isolate my dx. I'm going to say, okay, dx is the same thing as du over 2. So then I can go and just kind of replace item by item. So then this integral can be replaced with the square root of u times du over 2. I plugged in u in place of 2x minus 1, and I plugged in du over 2 in place of dx. So I can see that I have this constant 1/2, right, being multiplied to the du. I can pull that out. I can pull out the 1/2, and I just have the integral of the square root of u du. So no problem. That extra 2 is not an issue. And then I can just take the antiderivative of u to the 1/2 du and then multiply that by 1/2. So this would be 1/2 times u to the 3/2 divided by 3/2, because you add 1 to the power and divide by it, plus c. So that'd be 1/2 times 2/3 times u to the 3/2 plus c, which is 1/3 u to the 3/2 plus c. And then I just take my expression for u, the 2x minus 1, and just resubstitute back at the end. And so my final answer would be 1/3 times 2x minus 1 to the 3/2 plus a constant. So in example 5, my eye is kind of drawn to the sign because I can think of this as sine of 3x squared times cosine of 3x. And so I can let u equal that. U can be sine of 3x. So my derivative would be, the derivative of sine is cosine. Well, that's perfect, right? There's a cosine there, so that worked out fantastic. But then I do need to multiply by 3 because I do need to use the chain rule. And then all of that is multiplied by dx. So let me just write this like this. The derivative of sine of 3x would be 3 times cosine 3x dx. So I would want to isolate the dx. I'm going to divide both sides by 3 cosine 3x. And I'm going to say that du divided by 3 cosine 3x is equal to dx. So I can replace in my integral the sine of 3x with u, and then I can replace dx with du over 3 cosine 3x. So my new integral will be the integral of, I'm going to replace my sine 3x with u, so I'm going to have u squared. I have the cosine 3x that's there, because that was being multiplied to the u squared. And then I'm going to replace my dx with du over 3 cosine 3x. And this is in the denominator. This is in the numerator, this cosine 3x, and then this cosine 3x in the denominator. So I can cancel that out, which is perfect, right? Because the term that had the x in it went away. I do have this additional constant. I do have the integral of u squared times du over 3, and I need to think of that as 1/3. So I'm going to take that 1/3 and pull it out of the integral. And then now everything inside is just all in terms of u. So this is ready for me to take the antiderivative of, just using the power rule. So 1/3 times u to the 3rd over 3, right? Because you add 1 to the power and divide by that, plus my constant of integration. So u to the 3rd over 9 plus c. And then I just have to take my expression for u and then just resubstitute it back in at the end. And I get sine of 3x cubed over 9 plus a constant, or you can think of that as sine cubed of 3x over 9 plus a constant. So up next is another really special case of U-substitution where it's not at all the typical type of U-substitution. It requires us to think about it and use it a little differently, but it's really cool. It's like I feel like it's a U-substitution loophole, or like a little twist on a U-substitution. Okay, so here we go. So I still am drawn to the inside of the radical as u because it's the inside of a function. So I'm going to let u equal that 2x minus 1. My du is then just equal to 2 dx, and then if I isolate dx, I get du over 2. Okay, so all of that is fine and good, but when I go to replace it in my integral, I do have an x that never got substituted out with a u, right? This 2x minus 1 I can replace with u, this dx I can replace with du over 2, so that's what I'm going to do right now. But we've got a problem right there. There's an x in there and I can't integrate with this extra x. But in this type of situation, what I can do is I can take this u expression, right? This is saying u in terms of x. U is equal to 2x minus 1. But what if I got x in terms of u? What if I said, okay, if u is equal to 2x minus 1, then x is equal to u plus 1 divided by 2. And both of those are saying the same thing. These are both saying the same thing. It's just that the one that has u alone is in terms of x, and the one that has x alone is in terms of u, but this is like the same relationship between u and x. So I'm going to take this and substitute that in for x. So now this is what I have. I have the integral of u plus 1 over 2 being divided by the square root of u times du over 2. So let me simplify this a little bit. So I can think of this as u plus 1 over 2 times 1 over the square root of u, because this is the square root of u over 1. I'm dividing, so I flip the denominator and multiply by its reciprocal, times du over 2. So I can see that I have a 1/2 here. I can also see I have a 1/2 there, and I can pull that out. That would give me a 1/4 outside of my integral. And then I have u plus 1 over the square root of u left inside. Now you might be thinking, so what? Big deal. I still have this complicated function that I can't just take a simple antiderivative of. And I will argue, oh, but we can. because look what I can do now that I couldn't do before. I have a common denominator. I have a single term in my denominator. So I can now split this fraction into 2. I can think of it as u divided by the square root of u plus 1 divided by the square root of u, because if you have a common denominator, you can split the numerator up, right? This over that over that. I couldn't do that before for a couple of reasons. One, because there was a subtraction under my radical sign. I can't split a radical over subtraction. But even if I could, I can't split a denominator over subtraction either. So what we effectively did by taking the inside of the square root and making it one variable, and then solving later for that variable, is we basically put the addition into the numerator. Before, it was a subtraction in the denominator. We turned that into addition in the numerator. Before, it was like a subtraction under a radical. Now the thing under the radical is a single term, and I can go ahead and split this into 2 different fractions with that common denominator. And then, because they all have a base of u, I can think of these as just powers of u. This is u to the 2 over 2, and this is u to the 1 over 2. Maybe I'll write that for a second. So u to the 2 over 2 divided by u to the 1 over 2, and this is just 1 over u to the 1 over 2. I can subtract these powers. So 2 over 2 minus 1 over 2 is just 1 over 2. So then this, the u over square root of u, just turns into the square root of u. And then this is u to the negative 1/2 du. And then when you're adding terms, you can just split the integral over addition. You can split integrals over addition, which is great. Just make sure you distribute that 1/4. So the first one would be u to the 3/2 over 3/2, and then u to the 1/2 over 1/2 plus c. So then that would be 2/3 u to the 3/2 plus 2 u to the 1/2 plus c. Distribute my 1/4. So that would be 1 over 6 u to the 3/2 plus 1 over 2 u to the 1/2 plus my constant of integration. That's my answer in terms of u, and then all I have to do at the very, 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 very end is take that 2x minus 1 that I had said u was equal to earlier and take that down here and resubstitute that back in for u everywhere that I see a u, and that's my final answer. So my antiderivative of that integral was 1 over 6 times 2x minus 1 to the 3/2 plus 1/2 times 2x minus 1 to the 1/2 plus my constant of integration, and that is my final answer for that last example. And again, if you're feeling like, I don't know, I'm not sure about this answer, you can always take the derivative of it, simplify that derivative a little bit, and see if it would get you what was inside the integral. So I will tell you that that's what would happen here if you were to try that, and this is our final answer here. So I look forward to practicing these with you in class. See you then.